Hello everyone, welcome back to another episode of Flying with Spurts. For my first viewer request, I received this question. Hi Spurts, I have a DCS question for you, or at least an evaluation. When you get a little free time, can you take the F-14B out for a spin? Be at 5,000 foot altitude, standard day, with 4 AIM-7, 4 AIM-9, full gun ammo, aka 56,220 pounds, and pull a maximum performance turn from 6.5 G and 0.49 indicated Mach number down to about negative 100 foot per second and 0.23 indicated Mach number. I would like to know just how many degrees of turn you're able to get out of it. I did the FPS equation and I came out with around 114 degrees of turn. I basically estimated that peak instantaneous bleed rate would be about negative 1200 feet per second. And I included here the diagram that they sent with the request, where they even put a little red line over the area that they're concerned about. So I had to dig around a little bit to make sure that this was a maneuvering flaps working and not one with them disabled, and it is. I came to a slightly different idea of what the negative FPS should be. I figure that it's probably closer to negative 1,000, but it is kind of hard to tell. So it's neither here nor there. Now, let's talk about some of the things that we see here on this turn chart. Here, let me blow it up a bit here so that we can read it a little easier. We see that this has a assumed limit of 6.5 Gs, which of course that was only a placard limit and was not actually imposed by anything on the airframe, and all the way through the end of their life, Tomcats were pulling much more than this. We also see a maximum lift line. Because the Tomcat does not have a fly-by-wire system, it's hard to know what the maximum lift angle of attack is. And it's even harder to control it. So I'll do a couple different variations of this test, and we'll see what shakes out. Now, some of the interesting notes is this little dogtooth snag thing right here about 0.6 Mach on the piece of S lines where it goes up sharply. From what I can see, that's where the maneuvering flaps employ. So the quick downturn in the piece of S lines is when the maneuvering flaps are inoperable. So now, on to the test. Here we have our lovely F-14 Tomcat. You can see that I have it set to exactly 55,620 pounds, 4 AIM-7s, 4 AIM-9s, full gun ammo, and I will be at 5,000 foot standard day. As a reminder, for this test, I do have unlimited fuel on, so that fuel burn while I'm on afterburner will not impact the data we're gathering. So we go out and give this a few wind-ups. Boy, did it feel good to fly the Tomcat again. Now on to the data. Okay, first we'll do the visually identical turn chart. The values in the gray lines represent the values from the graph itself. And we have the blue line which was me attempting to hold 25 degrees indicated angle of attack, or units. We'll go with units. Me attempting to hold 25 units. A little bit of noise in the data. Again, that's just the nature of the beast. But we can see that this instantaneous turn rate I achieved was not high enough for any given speed. So I went back and went ahead and did a 30 unit pull. And sure enough, that instantaneous turn rate matched up very, very closely with what we would expect to see. Now, we notice that the sustained turn rate is a little bit too high on the back end. We'll come back to that. Ultimately, the question was, how many degrees of turn would I get going from 0.49 Mach down to 0.23 Mach? Well, I couldn't actually get down to 0.23 Mach. The turn I was able to get ended at about 0.25 Mach number. This was still around negative 100 feet per second piece of S. So in a sense, I reached the same point. But because I had a higher average turn rate, I ended up turning more degrees. I wasn't bleeding speed fast enough to get down to the lower turn rates fast enough. So as a result, instead of the requester's 114 degrees, I achieved more about 145. And we're going to come back to the sustained turn lines in just a moment. First, I want to go over the piece of S plots. On the lower half of the graph, we see the deceleration plots, starting at a little over 0.7 Mach at 0 piece of S negative, and that's right around where the sustained turn line, the piece of S0 line on the chart to the right, matches up. And then we see it spike all the way down to, this is where I had my assumed negative 1,000. Come to think of it, if I assumed that it was negative 1,200, it might be more consistent. So maybe the requester was right. I looked at where the different piece of S lines hit the back end of the curve, where they hit the red line, and did my best to try to figure out what Mach they were. Unfortunately, these charts are really imprecise for that, but I did my best. But by and large, you can see that even a little bit of human error on my end, moving the line, a tenth or two left or right, the gray line, a tenth or two left or right, would not impact the fact that the negative piece of S we should be having at a max pull at any given speed is not what I was experiencing. So we're getting the right lift, but we're not getting the right drag, is what it appears to be. Now, let's go back and have a look at the sustained turn line plot. So on the sustained turn line plot, if you start on the right end and start moving backwards along the speed, you see that it starts off a little level, then it spikes up. That spike up is where the maneuvering flaps begin to employ. That's also the region where I'm experiencing too much sustained turn rate. So I think what's happening is that the maneuvering flaps, as implemented currently, don't generate enough drag on their own. Making a flight model is extremely difficult. It is so hard to get things to change to be just right. Now, there's little tweaks here and there that, are still happening. The F-14 is not considered done. It's not out of early access yet. And even if they never get this issue corrected, I don't think it's really a game changer. It's not a deal breaker, because if having those extra, degree and a half, 2 degrees of turn rate, of sustained turn rate, is what's going to be saving you at 0.3 Mach, then you're not flying the Tomcat correctly in the first place. You don't want to be living at 0.3 Mach. So while it's not perfect, I don't think that it's a big deal. So if it gets fixed, great. If not, I'm not going to sweat. I also did an acceleration run, which we see here on the top half of the piece of S-plot. So once again, we have the gray line representing data pulled off of the chart to the right. We see the pale orange line. It may show up as yellow in YouTube, I don't know. But the pale orange line represents a smoothed out version of the acceleration data I got. But what it shows is that I had a little bit of a lag at the beginning of my acceleration, and that may be due to having too much angle of attack on the plane as I was trying to level out. But we see that for the most part in the subsonic, it follows really closely. And in the transonic, it starts to divert. We see from 0.7 Mach to about 1.05 Mach that we're pretty far off. We're starting to get decently far off, a little over 100 feet per second. Now there's a known bug in DCS that I talked about in my Viper FM video where the weapons have too much transonic drag. So with having 8 missiles on board, that's fairly well representative about what the problem is we're seeing. But notice that once we get above that transonic region, once we get up above 1.05 Mach, we once again start more closely matching the data. All right, I guess that about wraps up this video. Thanks for watching. I'll see you next time.